This magic story happened in Seattle. 25 July, project Kamen, another project. This movie will show you test result of best project in free energy motors Hunter. Sponsor of program Svetlana Konzen and Douglas Konzen. Director of stage Svetlana Konzen. There are 6 rings of knowledge. The 6th ring is 15 of salt gold. You must understand all 5 rings of knowledge first. To get to that gold ring of knowledge, some may be fake rings of not fit. Enjoy the video and write what you think.
Okay, well, that's what that high heel shoe is all about. Anybody was wondering. So, this is a photograph of the scope, and it's the output from the secondary with the cap over it going into the load of that light. And if you saw the previous video, you see that there's just a little glow in the light because it's only about 23 volts going into it. But the light actually gets quite hot. It gets hot. So there really is some power going into that light. It's not 120 volts, it's only 23. So where we left off, I was adding more and more capacitance across the load and the secondary of that transformer, the 3-phase transformer core with the A phase is the secondary output, the B phase is shorted, and the A phase is primary, which just has the 120 volt grid put into it. So what we have here is the current, which is this. See, it kind of takes a dip there. It's starting to saturate the core. I guess that's what that means. While the voltage is a pretty smooth sine wave going on. Now, we know that the voltage is about 23 volts. This represents 23 volts. The current at this time with this has 72 UF across the load. And this was 0.61 amps, 610 milliamps. And when I got it up to 132 UF plus another 30, it became 162 microfarads over the load in the secondary. And now the current here had pretty much doubled up to 1 amp and 350 milliamps, 1.3 amps. And on the scope, I took some video and scope shots of it with 165 UF, and the current on the scope doubles. The peak to peak, it's not here anymore, it's way up here. And the voltage just goes barely up, just like I was seeing with the meters. Okay, so while we're staring at this, when you want to do a scope analysis, or whatever you call it. First of all, you want to have the zero line right here. Is that the zero line? Here's the zero line across here. You want to have it peak, zero line to peak, and zero line to peak exactly in the middle. If you don't, you'll get messed up readings. Okay, this is pretty good. It's like 2 above, 2 below. Now, next thing you do is you count. Each of these squares has tiny spaces, 5, 1, 2, 3, 4, 5. Those are called minor square divisions. I just call them spaces. So anyways, you count. You see the cycle of voltage here. You count from the zero line all the way over to the other zero line, okay? So you go zoom, zoom, and then there. And you count, that's one cycle. That equals 360 degrees. Okay, so, and if you know how many spaces or minor square divisions are exactly between this 0 point and this 0 point, now you can divide 360 by that number of spaces. And this happens to be 27 if you count. From here to there, it's 27 minor square divisions, okay? And 360 divided by 27 comes to 13.3. So that means that every one of these these 5 square divisions in between a larger square, each of those little spaces is equal to 13.3 degrees. Okay, so now you look at your phase shift. And note this is capacitive leading. This is the current. This is the inductor. You can call it that. This is the current, this is the voltage. So what's happening is this gets hit first by the power, the energy coming out of the secondary, because it comes first. And that's what I've been saying in my arguments about what's going on, is you fill up the capacitor first. The capacitor gets filled. If it gets filled all the way, that's good, because what's going to happen is when the change in direction happens in the AC, the capacitor is going to discharge. And that's the power you get. Now, this one I calculated at 66 degrees here. And you can look up, you go to Google or something and you say, what is the cosine of 66 degrees? And I can't remember what it was, but that's what the power factor is. And so when you do volts times amps, then now you throw in the power factor at the end. Now 90 degrees is 0. Power factor 0. So technically with a sine wave, dealing with sine waves, technically it's 0 watts at 90 degrees. So, but when you put something into ferroresonance, when you put that core into ferroresonance, and this is what puts the core in ferroresonance, you have even a stronger, a wider phase shift between capacitor coming first, volts coming second. And so you're when that capacitor discharges, it really slams the core, steel laminate core in these transformers. It slams it hard. Uh-oh, what happened? And it slams it really quick, really knocks it hard. And then upon the cap discharge, you have one polarity of magnetism in the core. And then when it's over with, you've saturated the core, I guess, so that's what it would be. Now the core flips polarity. And you start the cycle again. So there's the ferro resonance. As far as I understand it, what ferro resonance is the core. And it's a mechanical sort of thing. The core is flipping itself back and forth, north and south magnetism. A very strong force. And that is what induces power. So anyways, been staring at this for a while. Try to get this over with. So with a 90 degree, so if you have a space here of like 6.5 or 7 spaces between the phase shift here, that equals 90 degrees because it's 13.3 each little space. Now, more to confound you some more, if you look it up, does a capacitive leading phase shift return to the source? You can ask that on an AI program, and it'll say yes. The energy stored in the capacitor upon the change in polarity, at that point, it will discharge back into the source. And the source in this would be the primary. So this is kind of how it works. When people want me to separate what's going through the capacitor and what's going through the load of the light, well, this kind of tells you what's going on. This is going through the capacitor. And what's going into the load of the light will be the energy stored in the capacitor upon the change in polarity. Okay, one other thing I want to say. So this is very interesting. You don't have power. This is not power. This is just current showing on your meter. This is current flow. This is not power over here. This is just voltage showing on your meter. Only the overlap is power. So here's the zero line. The only power here is this area right here. And the other side of the sine wave, it's this right here. Other side of the 0 point, I mean. So this is where you get deceived. You think you have all this power because the meter shows all this current and the meter shows all this voltage, but the only time it overlaps is right here. And you can't have power without both volts and current at the same time. Okay? So what you do is you calculate this power. And see, it's kind of a triangle. So what you do is you put yourself in a DC mode and you count, like this is like 7 spaces high. And you take an imaginary triangle like this, turn it upside down, stick it right next to it, and now you'll have a block of DC power where this is how long it lasts right here. I believe this is, I'm not sure what it is. I think it's 14 milliseconds or something. But anyways, you can look on your scope, see what your time setting is and how long this lasts right here. And now you have a block of power, goes up, comes down, and you can say how much power is in this DC block. At the end, you subtract it, you divide by 2 because you've added an imaginary triangle just to make it into a DC block. So anyways, so now you go to one cycle, like from here all the way to here. See how long that lasts according to counting the minor square division. See how long that lasts in milliseconds. And then you know how much power you have here and how long that lasts in DC. And so now you have a percentage of on and off time. So first imagine it's one solid block of the whole cycle of DC, and then find your on-off time percentage, on and off time percentage, and throw that in there. So if it's only 20%, it's only 20% of real power. So this is just on the positive side of the zero line. Since we're AC, you do the same thing down here. Okay, so that's how you figure power from a scope. And there really is no argument about this. Although I'm sure there is. So there, this 90 degrees though, when you have 90 degrees, things get weird because supposedly it's no power at all. But what this shows, when this goes to 90 degrees, now it is at 90 degrees when I shove all those more capacitors across the load all the way up to 100. This is only 72 microfarads. When I go up to like 162 microfarads, now this is a little bit over 90. I had 93 degrees phase shift. And some other scope shots I saw of these transformers with like 120 volt input. Whoops. I don't know what the heck that is. That's good enough. I'm going to pause right now. Okay, now I'm back out here. So what I wanted to say is if you have a 90-degree phase shift, it's capacitive leading. That means, like we just saw, the capacitive trace comes first on the scope, which means you're filling up the capacitor first. When you have 90-degree phase shift and capacitive leading phase shift returns to the source, that means all of everything in the capacitor returns to the source because it's 90 degrees, if that makes sense to anybody. So this backs up my pretty good theory that the way these work is the capacitive leading phase shift extreme puts the core into ferro resonance. And the ferro resonance of the core is what makes so much power into the capacitor from induction into the secondary. In this case, I'm looking at the secondary out. And the ferro resonance puts, I guess you could say, more power than you think possible, filling up that cap. Quick, too. And then upon the AC flip over, it discharges. Just like, look at any AI program. Go Google it. Capacitive leading phase shift returns to the source, returns energy to the source. Okay. So I think what you saw in yesterday's video, where I keep adding more and more capacitance, it makes the phase shift bigger on the output to the load of this light. And then when it flips over, it's like a switch where the capacitor discharges into the load. And it does that 60 times a second because we're at 60 hertz. And the back EMF from the primary here, it goes right past the shorted out B core, comes in the top of here and comes out the bottom. The back EMF, think of it like a magnetic ball of electromagnetic energy going in opposite direction as the current flow, initial current flow. So it comes around here and it shoots past this because it's shorted out, and now you happen to have, like, let's say a north here, you happen to have a south here, so that magnetic ball of force field of back EMF gets sucked right over here, and now it shoots down through here to the south end. And maybe someone can help me with this, but I think it flips polarity after, if it comes in here south, if it comes in here south and the coil's north up here, when it gets through the coil, it has flipped polarity, so it's now north shooting out of here because it's back EMF, and it when it comes out of there, it's now another charge of back EMF has been created from this coil. And so you have a north, let's call it the second ball of magnetic force field, comes shooting out of here, and it gets pulled with great force to here, because this is south, because this started out north and south, and because this is shorted out, it just shoots right by. There's no magnetic polarity to this core here. You could call these shunt bars magnetic shunt bars. It's shunting the magnetism around the core, if that makes sense. So the back EMF comes out like this, goes down here, goes like this, and it returns. When it returns, and remember the technical side of things says that 90-degree capacitive leading phase shift returns to the source. Well, it's all returning to the source, isn't it? And because it's back EMF, it's of opposite polarity, so it gets sucked into the back end of the primary. And there you have it. So you lower the draw. That's why yesterday when I added more capacitance over the load, it made more and more phase shift, and it got to be like around 90 with really high UF value. And so when this back EMF enters the backside, gets sucked into the backside because of magnetic attraction. If this is north, this is south, it's going to go right in there. It not only reinforces power being made, it because it's a stronger magnetic field, it also displaces what is coming in. Okay, so it lowers the draw. That's what we saw on the video before. Okay, I'm going to call it good. Bunch of talk today. Okay, thanks for watching.